All right, thank you, Corey, and I have no changes to add to that. I'm pleased to be here at John Locke giving this presentation. And good afternoon to everybody, and welcome to this talk. I hope you enjoy it. I hope we both enjoy it, myself too. I don't expect I'm going to be able to make anybody into a good climatologist in 50 minutes. You know, it's pretty tough field. It's a lot of things going on. But I do hope to develop an interest and a knowledge that you can make use of and will make you want to learn more. And this is going to be fast-paced. So please, if I may ask, stay with what I'm saying, not with something else you might be reading. You know, my foils are somewhat overloaded because I had to slash them to do this in 50 minutes. Don't read where it's slashed, please. Okay, just stay with me because then you'll get more out of it. You can always order it, and you'll get the whole talk. You'll get the 100-minute talk. Okay. All right. So we'll put on the seat belts and we're ready to go. It's going to be, for me, it's going to be like what the Red Queen said. You know, you got to keep running and running and running just to stay where you are. That's what I'm going to be going. I'm going to be going fast. Okay. So here's the preface. Here's what I got to do for the preface. Okay. It's obviously a topic that's important and contentious at the time. And there's expectations of spending $50 trillion on this over the next 20 years to solve this problem. Okay. And so I'm promising you this. I want to read, I want to state that very clearly. That's absolutely true. I'm going to have no political commentary. It's totally objective analysis. I developed all of this myself personally. I talked to people, but it's all developed by myself. There's no funding from business or industry. And nobody in this room gave me any money. And nobody gave me $500,000 to come up here to say, hello, what can I do to help you? So nobody gave me that either. So there's multiple interactions that are subject to precise quantum mechanical probabilities. But these are probabilities. They don't allow runaways. Physics does not allow runaways unless you can put it into a bomb. But physics, as it's made by nature, does not have runaways. And I'll present you with a unique approach. OK. Caveat. This slide sequence is not a novel, but I do have a progression. And if one is presented with new information, the best way if you want a jury is to do this. The best way if you want to listen to me well is to avoid clutter that's already in one's brain, is to just accept the new information you're getting is possibly true. Afterwards, decide whether it's junk or not. Okay, but if you listen, accept things at first with whatever kind of skepticism, but at least to listen. Anyway, so I violated a cardinal rule of a good presentation by too many words on some slides, because I'm going to use this slide presentation other places. And I have blue slash lines on some of the slides. And so it's going to be difficult to avoid candy that's placed in front of you. But please reinforce my spoken words by reading only the related written words, not what's covered up. So don't read that, OK? But enjoy reading everything else, OK? OK, so the next slide is the outline. And I don't want to keep going back to it, but it's on the board here. And I'm pretty sure you can guess exactly where I am on the outline as I go along. So let me see, what do I want to say? That's about it. I'm going to move on from that. So you can be able to figure out where I am. So here's the learning objectives. There's a table here of information. And let me see, I've got to keep up with myself here. I want to have some new knowledge for everybody. I'd like you to walk away with something more than something, I hope. I'm going to explain basic mechanisms. The basic mechanisms are absorptions, adiabatic effects, blankets, convection. You probably know what 3 or 4 of those mean. Only adiabatic, some people won't know. The rest of it, what you think it is, that's what it is. Okay, but it's used in a special way with quantum mechanics. I'm going to try to say why CO2's absorption is limited. It's just not going to run away. The versatility of the novel approaches that I've employed, the dominant role of water. Water is everything. Water is changing all over the place. CO2 is there. It's everywhere the same. Water is volatile. Projections and the need to be verified, which we're not doing, by going back in time. And modeling issues that probably need some better assessment. Oops, we should use this. OK, there's much that we want to know. Basically, we want to know what the truth is among all the energetic opinions on here. I'm not coming to you with either side of the story, so I don't get any publicity. I won't get any publicity. I'm not way over on one side and way over on the other side. CO2 is warming things. It's just not as bad as you think. That's where I am. Ah, boring. Okay. So I mean, I'm not in a fight with anybody. It does do things. And so just to make sure you get the big picture, the final picture you want to know is what is CO2 going to do to us in the long term? That's my last slide, so it's going to be my next slide too, just so you buy into what I'm saying. This is a slide that everybody in science does. They do a log 2 of CO2 with reference to a reference. This starting point is for the temperature of a starting point, which is what the climate was like a couple of years ago, and 380 parts per million. And then you say, OK, I'm going to make CO2 get more and more. Every factor of every unit of 1 here is a doubling. So this is 1, this is twice as much, this is 4 times as much, this is 8 times as much. Okay, that's our log curve. So what it solves is how much change in temperature do I have if I change CO2 by this amount? That's the way you look at it. They used to look at it linear. That's hogwash. It's this the better way to present it. Okay, what I get is 1 degree centigrade per doubling. It's about 1.04 on this side of this center point from 2 years ago, and it's 0.096 on this side. It's about 1. And the IPCCs, their numbers are 2 and 4. Okay, so naturally, their numbers look a lot better, worse. But what I do is I look backwards here. Their numbers don't look backwards. We do have some data, you know, from the last 50 years. So when I go backwards, this looks pretty good. Okay, their numbers are, you know, they're way off, way different. Okay. Some preliminary. I got this, and I'm going to just go this. This was my original. What's happening here? These are my notes to myself, but it's easier for me to do it this way. Is power. I want you to know what power is. It's energy, power and energy. Energy is in watt hours. Everybody knows what kilowatt hours are. You know, it's in your electric bill. And a kilowatt is the energy rate of 1 kilowatt per hour. That's the good way to remember it. Okay. And we're about 100 watts. That's what each of you guys is. You're putting off 100 watts. If you're running around doing a lot of stuff, it's 300 watts. But by our living standards, we have 11,000 watts dedicated to us. That's kind of what business does. So you can look at your electric bill and say, how much is that? Well, it's a few kilowatts. It's like, and anyway, so that's the watts per square meter. That's the flux reaching us. The sun's average is 240 watts per square meter. The blanket addition of greenhouse gases is 150. That 390, for this example, has to escape from the Earth every single day, or else the Earth gets hotter. If you add more coming in from the sun or from CO2, that sum goes up. If that sum goes up, the Earth's got to let it go out. Its temperature's got to go up. It's as simple as that. You put any more in, it's got to come out. If it's got to come out, it's going to make the surface hotter. And temperature is in Kelvin or Celsius, and Kelvin is 273 plus the Celsius. Kelvin is 273 plus Celsius. Okay, there's some big numbers. I don't want to get all tied up in too many big numbers. The number everybody wants to know is how much CO2 is in the atmosphere. You probably read this is a number that's published, 3,200 gigatons. That means 3,200 billion tons. Sounds like a lot. Okay. Well, the whole weight of the entire atmosphere that's giving us our atmospheric pressure is 5.5 million, gigatons. It's quite a bit more. So, it's a big number, but it's a big number. All right. Where else I want to say? Oh, Planck body radiation. Planck body radiation is the radiation if I have, like sun. I don't want to explain what black body means. It has a meaning, but it would take me too long to say. It's a good reason why it's called black. But the sun is a black body radiator. And it has a distribution. You can see the colors. But it's got colors in the ultraviolet that you can't see, and it's got colors in the infrared that you can't see. So I'm going to look at this infrared region that the Earth, when it's giving up its heat, its temperature, it's in the infrared. I'm going to call them colors. I look at 150 color bands. If you look at the sun, you might think there's 6. Well, it depends on how you cut up the pie. Well, I cut up this pie into 150 color bands. And then can individual photons be tagged? No, 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 this isn't a pull game. It's not a pull table. You follow the orange ball on where it's going. These photons come and go because quantum mechanics says that we can explain what we're doing by making believe there's these photons and they're there, and they'll be the right number when you do the math right. You'll get the right number of photons, but you're not following any single photon. Okay, I don't want to show that. Okay, this one here. Cross-section parameters. This is a good one to look at. Let me see what I have for that. What you have here is that what did I do? Here we have our surface of the Earth is here. It's shown as a curvature, but you know, for the height I'm interested in, which is 13 kilometers, which sounds like a lot, that's nothing compared to the radius of the Earth. So for all practical purposes, for any calculations I do, the Earth is flat. Believe me, it's flat for any measurements. But anyway, it is technically this. This is 0, and it's 390 watts per square meter coming off. That's what comes in, that's what comes out. And so at this C of 13 kilometers, why did I stop there? Because I'm going to call that the pivot point. Beyond that, it's sort of like the Irish would say, beyond the pale. Beyond there, that's where all nasty things happen up there, because there's no ordered structure to the molecules. That they're in thermal equilibrium. Up there, it's every man for themselves. And a molecule gets hot, it can't find anybody to mate up with to lose its energy. So that's where the cutoff is, around 13 millimeters. And so at that point, the temperature tends to be, the power tends to be about 100 watts per square meter. Whatever it is down here, 390, it's going to be 100 there. Okay. And just so I say this now, because I don't want to spring it on you later. Later on, I'm going to call that 13 kilometers. I'm going to call it, as a normalized number, it's going to be 0.82. 0.82 means that 82% of all the molecules are below 13 kilometers. And that's the way I do my analyzing. I don't do it by kilometers. I do it by the fraction of molecules that are in my new scale. I go from 0 to 1, not 0 to infinity. And it works out so much nicer. Okay. All right. I keep on. Some additional facts. You might say, well, suppose everything weren't peeling off like that. Suppose it all was at atmospheric pressure. It won't do that. Physics won't allow that. Believe me, everything that's happening in the atmosphere, you don't have to measure it to know it. If you were a good scientist, you can calculate exactly what the temperature should be at every altitude, exactly what the power flow should be. You can calculate it all. But anyway, but suppose it were that. It's about 8 kilometers. So that's how much all 1 million parts per million would be. But if I took the 400 parts of CO2, they would be just over 10 feet. So all the CO2 that's in the atmosphere is 10 feet tall. But, you know, but how many atoms is that? That's like, that's like 100 million trillion, no, like 100,000 trillion molecules per square meter. You know, it's a lot, or totally, I mean. So anyway, so it's these thicknesses that for varying CO2 ppm that provide the basic transmission table. So when I'm finished, I got to find out how much is being absorbed by the CO2 in the atmosphere, along with all the water that's in there, along with other things that might be in there. So I have to go to some tables for CO2 and hydrogen and water. And those tables are based on the colors that I was talking about. So I have the transmission for each of those. Okay. And okay, here the water is 10,000 parts per million, but it doesn't really absorb as much as CO2 does. It absorbs not at the higher energies, but at the real low energies. It absorbs a lot there, but it doesn't absorb at the higher energies. And they don't talk about it reducing it to a gas at atmospheric pressure. The way they do it is H2O. Make believe it all the water in the atmosphere as vapor turned to water. The average thickness is 1.7 centimeters. And when you look at that and you multiply it by 60, because the turnover in the rain is like 60 times a year on average, you get 102 centimeters, that's a meter. You get a meter of rain every year, average around the Earth. And it doesn't change. Okay. Anyway, so what did that come to? It comes to 500,000 cubic kilometers or 125,000 cubic miles. That's a lot of ice carving, you know, carving, whatever you pronounce it, of coming off of ice flows. Because you know, if the iceberg melts, it doesn't do anything. Okay. But we're only getting 0.1%. We're only making as much energy as this. The tropics are spending 10%. So, okay, so I'm going to look at these effects here. Planck emissions basically have covered it, I think, to the extent that I want to cover it, let's say. Let me see if I get to there. It has a smooth, quantum mechanically defined distribution. And if I go to a higher temperature, I get another pattern. And each of these distributions are like nesting dolls inside of each other, you know. The lower temperature dolls fit inside the higher temperature dolls, these profiles. So it's smooth. And it has a function of what I'm going to call infrared color frequency. So the Planck emission then is the upward directed heat that in the Planck, this is the definition of the Planck black body. It's the equilibrium upwards directed heat, including the profile, that directly matches the incoming flow from the sun and the blanket. And the area under that distribution is the watts per square meter that the whole Earth is giving off. So that whole distribution is replaced with a flow for the whole picture, watts per square meter. Okay, and so each additional 1 degree, this is a good number, each additional 1 degree C adds, 1 degree C is 5.4 watts per square meter. Okay, absorption. Oh, I already had that. Okay, absorption. Except for windows of transmission where nothing gets absorbed, nearly all the BBR photons are absorbed before you get to that 13 kilometers. It's not like you captured a bullet, though. You know, it doesn't stay there. It's not like an electron or an atom. It's a photon. It's something that's running by at the speed of light, and this atom and the CO2 molecules. I want some of that, and it takes the photon, you know. And there's like the probability of it capturing it, and it will capture it. There's a lot of photons and there's a lot of molecules. So it's like a tuning fork that you have in your house, and you do this, and your piano starts going ding, 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 right? That's what it's like. It's no particle hitting it. It's a photon. All right. CO2 is especially receptive. Its reception is right in the middle of the distribution that the Earth is giving off. That's why it's been good to us all these years. All of a sudden, it's not so good to us in our mind, but it's been good to us. Okay. And the absorbing molecule, when it takes in this extra energy, it's said to be excited. It just takes it. And now it's there, and it's like, I get too much energy. And it forgets about momentum and all that, and it just lets the energy go, and it spews it in isotopically. So what happened here? What was a photon going in this direction becomes photons each time it's different for each absorption that are going in other directions. So half of the energy is back. So half the energy comes back, and it's the seed for the blanket. So that's the seed for your blanket every time you have an absorption. Whatever is going on, once the molecules are already in equilibrium and they're bouncing and they're interacting and they're doing photons. Hey, every time they have an interaction that was isotopic to begin with, and now it's isotopic afterwards. This one, it's like it was directed, and now you've split them. So it's the seed for the blanket. So absorption is simple, but that's the little extra kicker. The adiabatic, what happened here? I went backwards, didn't I? The adiabatic effect. Now this involves transitions between thermodynamic states. Thermodynamic states are pressure, volume, and temperature. And that's in the lower atmosphere. That's the ideal gas law if you had that in your high school chemistry. And the adiabatic effect is, if you just memorize this, sort of is the way to, it's a process from one PVT to another PVT in which work is being accomplished, but which there is no transfer of heat to or from the surroundings. Well, it's not like anything comes from nothing. So the work energy is being withdrawn, from the change in the thermodynamic state. So when, for example, the flux from the Earth comes up, it's coming from a hot region, it's going into a lower region of a lower density. That's defined in the work sense of expanding into this volume. So that's work. So pushing something into this expanding volume is work. So what happens? Well, this flow that was at a certain temperature keeps the temperature of its surroundings. It's like nothing happened. It just goes buoyantly on through. But it's doing work all the time. That energy goes away. You never see it again. It doesn't become infrared. It's gone. So that also acts to not create a feedback effect. It does not affect the blanket. So you get a free ride. 140 watts is always used up in that way. OK. This is a beautiful figure. I had to do it, but you can't. OK. This is the picture that you see everywhere on the web. You see variations of this. This is the Trenberth et al. Diagram. They worked on this in the 90s. That they worked on the zeros, and they're probably still working on it. It's very good. It leaves out some things, but it's very good. It's very good for me to explain things from. So in yellow, you have the I used the wrong thing. For the yellow, you have the sun coming in, and the only parts that matter are the 78 and the 161. They add up to the 239, which is what the sun is contributing on average. And then when it comes up, this is the part that's going up for this model of his, 396 coming up. Well, if it's 396 coming up and there's 240 here, I can tell you right off the bat what the blanket is. It's the difference between these two numbers, because if this came in and then the blanket comes in, it's 157, and then that's what this is. Okay. But I didn't take care of these yet. Okay. But anyway, so this is the 396 that comes up, and it goes up and it goes up, and now it's 239 up there according to him. Where is this number? Where's the thing? He doesn't put a height on it. Turns out that's at 13 kilometers. Okay. So what I was judiciously choosing is what everybody's choosing too. So it's anyway. So but it's got the wrong number there, because he doesn't want to mention. Apparently, they didn't want to mention adiabatic. Not that he forgot about it. The adiabatic effect of 140 watts per square meter is not mentioned. He just throws it into here. It's escaped. Well, 140 watts went away. But subtract that, and you get 99. What's the power level at 13 kilometer? It's 99. So that number should be 99. And you could have had a little wiggle saying, no, 140 watts just disappeared.
Who's the he here?
Trenberth.
Oh,
Trenberth et al. He's the main name on it. OK, so in the top of the diagram is the pivot point. Never identified as such. He doesn't identify the adiabatic, but it's a great diagram. OK, this corkscrew here is thermals. Now, if that was just heat that went up, that would be in here. Well, the thermal is something that it burns itself up before it gets any absorption. It's like a physical motion. So that heat is going up, it gets absorbed, and it comes back down through here. OK, so it's going to come back. It doesn't disappear, it comes back. But it's not part of the blanket. This one is evaporation, including from plants. So when you get evaporation, you get a cooling of the Earth. So this is cooling, but the Earth is giving 80 watts per square meter to cause the vapor to form. And the vapor goes up here, and probably it will condense and supposedly causes water, and it supposedly falls as rain, but it's warm rain. But it doesn't have to fall as warm rain. That heat comes off on its own, and that heat can go somewhere else. But anyway, so this is if everything is local, and this is supposed to be the thing for the whole Earth. So, I mean, if it's the average, somewhere it comes down. Okay, so it's for his view of things. I don't look at it that way, but it's true that it goes up and it comes down somewhere as water. But if it comes down as water and hot air somewhere else, it's changed the temperature. And in the temperate zone, I estimate it's making our temperature about 7 degrees warmer. Because in the tropics, it is 14 degrees cooler than you would normally expect. That heat goes off when the vapor turns into water again, way in the crown above the tropics. It gets all this heat. It could heat the water for the rain. It does heat it partially. But basically, it's a lot of extra heat. And it looks, where should I go? It sees those poles, and it goes, it heads for the poles. There's a lot of heat heads there. And we don't complain about that, you know. We're welcome to have it. It's a good thing. Okay, so I don't want to go through these numbers. You can do them on your own. It's easy to do. All the numbers come out right. That 333 and the 396 come out right. Okay, this one I can't show you. That's a beautiful photograph I went by. I just love it. The one I went by, there was the tent structure. I like it better than the trend berth, but I don't have time to do it, show it to you. Okay, further elucidations. Now I want to look at the 17 and 80 watt things. The 17 is straightforward. The 80, it depends on what it really does. So here's the 17. It goes up and it comes back with the back radiation. And there's the 80. It goes up. It's still local. And I'm not using trend berth. I'm making believe it's local. If it comes back and it all goes into reforming new water, it just keeps going back and forth. So it doesn't affect the blanket at all if it goes into these loops. Even though it's doing this exchange here, when it comes back, it's going right back to the same place. So that's a point of contention about whether I should ever count those things or not. So I go back to here, and I'm just showing this. Here I just take what he has. This 80 is going up here. It's forming vapor, and it comes back somewhere. If it's coming back here, it doesn't go into here, though. Does that make sense? Make sense? I hope. Okay. Okay. So now I'm going to look at what's happening. I'm a little bit into climate change now. I mean, a little bit. The following looks, I'm going to show a picture from space and then a look along the surface of the Earth, tangentially along the Earth. Now, at the top of the Earth, the sun and the Earth stir the pot at the top, and perturbations stir the pot near the surface. So the weather is constantly stirring the pot. I mean, the Earth is turning. The sun's coming on and off. You're turning the stove on and off, and you're spinning it around. It's churning. And what you have is you have a grand picture of churning up in the upper atmosphere. These are clouds. I mean, the clouds make it easier for you to see. I mean, but there's nothing. It's not the same picture tomorrow. 24 hours isn't long enough for it to come to a steady state the same way. If the nights were 1,000 hours long, we'd be cold, really cold all night. But it might start up the next day the same. Someday it might be the same. You might get repeat. But you don't get any repeatability on the 24-hour cycle, which is good. I mean, you get this weather change. Okay. But anyway, that's the way it is. So all this perturbation is turning at the top. Okay, now this next slide looks at, I'm looking, the North Pole will be to your left, the equator will be to your right. And you're looking from west to east. Okay. And there are 3 tubes. What are these tubes doing here? If you haven't heard of this, I mean, all the climatologists know about it, but I mean, most people don't. It's nature making a perfect solution to a problem that I'll immediately explain to you. Has anybody ever seen this picture? It's gorgeous. It's loaded with information. It's loaded with information. It's just made very well. Here's the equator. A boiling pot of water that's coming up. And then it's the heat. So look at this. Heat goes up. Where's it going to go? It's going to go that way and that way. Here's the cold air from here. Where's it going to go? It's going to go this way. Well, anytime it hits the equator, it's going to do some warming. As it goes this way, it does some warming. This way, it's going to do some cooling, right? Suppose this fellow wasn't here. You'd have this guy going up and this guy going down, and they would be clashing and fighting all the time. It would be misery. Okay? And there's nothing that says that couldn't have happened. But things shake out. There's a natural harmonics sometimes that show up that solve problems. So this thing is a cushion. This thing's anchored to the pole. This one's anchored to the equator. This one's a little sponge ball in here that solves the problem. The airflow is counterclockwise here, which means the energy's going this way. This one, the energy's going this way. This one, the energy's going the other way. There's actually airflow going that way here. And then there's the jet streams up here that are going that way too. Okay. But look what it did. Now these guys are in harmony. And by the way, a lot of this is adiabatic. So I didn't lose any energy. It just naturally went from being warmer to less warm, or cooler to warmer. It's adiabatic. So this cell is just a nice little cushion in there. And just the fact that they're going in different direction makes a wall here that's hard to broach. Now, in wintertime, you've seen the polar vortex, right? That's what it is. It's this wall being rubber banded around. This thing's fighting back. It looks like it should lose, but it takes the punches, you know. So it's really great. It's a great solution by nature. OK, so rain. Now I'm going to switch to rain. Rain totals have not been changing over many decades, believe it or not. Temperatures are going up, but the rain hasn't been changing. The following one, next slide shows that. Also, the average temperatures don't appear to have changed. And there's an intense correlation of rain with the latitude and the cell boundaries. If you look at that last picture, this thing, the relative humidity is really, the relative humidity is really low. I mean, this is Phoenix here. This is desert. This latitude is desert. And the desert isn't over here. It's right here. It's not over here. It's right here. And so you're going to get rain here, too. So you get rain here, and you get rain here. OK, let's see how much you get. Look at that. OK, so there it is. There's the rain. About half of it's in the equator, I guess. And the other two add up to something a little less than the equator. But, you know, that's it. And in between this, does that mean the temperature? What's the temperature there? Well, here's 60 years worth of data of temperature. And it's the same. For at least for this source of data, the temperature didn't change much over. You can look at little jiggles here. But this is guess what? This is the South Pole. This is the North Pole. What's going on here? Well, this is a rock down here, and this is a sea. And it's got ocean currents flowing into it. It's like a little pot that's cooking, but it's kind of cold, but it's hot by the standard you would think it would be. So it's a very gentle sea up there. And look, there's even going higher here. Okay, so this is the North Pole. It's totally different beast here. This is a big concrete slab. This is a lake or a sea surrounded by land. Okay. All right, now, where am I? How am I doing? I hope I'm doing OK. Convection. Am I doing all right? I hope you're with me, because if you could be learning some things by now. I'm not sure. Convection bus. I want to look at the convection bus. I'll have it. You can have it. I won't, but you can have a survey later. What figure did you like the most? I'd vote for the 3 cells myself. OK. The following slide addresses that 80 watts again. After this, I'll be off the Trenberth thing. His is an average picture for the entire world. And so since this makes it a closed system, one might expect there to be no external convection input. Well, because they're not. This evaporation is taking place inside of it. So, but fundamentally, there's no reason that the closed system can't have inputs and outputs that are different in different places. And that's what's happening with the water evaporation and the heat that's given off after the water condenses. And the drop-down must be treated locally as a mini-sun. When it's local, it's like a mini-sun if it doesn't go through a local absorption. So the stuff that comes down non-locally is going to add to the absorption, and it's going to add to the blank, and it's going to add to the temperature. Now, whether that happens back, remember, I'm saying it's going to add to it. But remember now, back at the equator, it went down by 14 degrees centigrade. So what I can't tell is whether this work that's been done is like giving us temperatures just for the whole world, or is it just giving it for the temperate zone? Okay, because, okay, so here it is. It's the same thing, same as before, except now there's a convection bus and it's dropping stuff off. And the back radiation, this is the simple formula for that other equation that if you go back and look at it from Trenberth, it's always 17 plus P0 minus X. And this one is, it's the P0. This thing's just P0. OK, so this 17-watt loop, it's just a loop. It does nothing. This one is an X part where it's local evaporation. It heats the rain, and it comes back. that 17, that x comes back here. But if 80 minus x comes off, that 80 minus x part ends up being part of the radiation here. OK, here's how convective flow happens. I've already explained it, but here's just a nice picture of it. At the equator, heat of vaporization, the water evaporates. The heat of vaporization cools the Earth. So you took heat out of the Earth. It goes up, it goes back into water drops. Gives off a lot of heat. Believe me, there's a lot of heat that's given off when water vapor goes into, it's, you know, if you turn water into steam, it takes a lot of heat. A pot of water takes a long time. Well, going the other way, it gives off that heat. The heat that you use to boil the water now comes off. Okay. And so the water comes off, and now this convection comes down the line, because it comes up and it says, where am I going to go? Well, I can heat some of the water coming down. Look, I know it's not doing that. It's 14 degrees unaccounted for. But it comes down here now, it drops some, may drop some of the water may come along, may drop some rain, and we'll drop some air. Drop some heat. Okay. Okay, this is a simple diagram. This says, well, so what? If at the tropics, it's 14 degrees colder, but tropics is only plus or minus, what is it, 23.7 degrees or something like that, latitude. How much of the area of the Earth is that compared to going from 90 to 0 to 90? It's 40%, because that's where the Earth is fat. So this just shows the relative area in each of these zones. So it's 40% in the tropics, it's 25.5 in each temperate zone, and it's like 4.5 in each polar zone. Okay? So the polar zones aren't that important anyway as far as the big picture goes. They're 5% important. That's significant. You want to call it important or not. It's important. But it's not equal to the other regions. Let me put it that way. Okay. So that's what's happening. This convection goes out and it drops itself off in my simple model. Okay, now here's a model that is really great. This is a great picture. It's so simple. This picture says this is what we would expect the watts per square meter, the watts per square meter to be at the two poles. This is the same scale. This is, again, this is the South Pole, and this is the North Pole. Now, did I do that wrong? I got them backwards, right? This one? No. Yeah, well, this one's what it should be, and this is what it... Oh, I said it backwards? Yeah. This is what it should be, and this is what it is. Okay. And so this is water that boiled up, and it didn't get to warm the water vapor that recondensed. It didn't get to warm the water coming down. It sent the heat off. Okay, and that shows up. Everything past this latitude here gets extra heat. Everything past this latitude here gets extra heat. And you say, wow. The thing that I find interesting is this little dip here. I'm just going to speculate. I mean, it's like this heat, it's getting out of there, and it really can't get far enough before it starts dropping right where it came from. You know, a lot of it's coming back. So it's shooting over here, but some of this stayed around. You know, I would expect this to be a maximum too, but it's not. It's probably. I'm sure the scientists are looking at that. I'm just saying that it looks like it's so much stuff. That could really affect the weather, by the way, the temperatures. Anything that happens to that shape of that curve is going to affect the temperatures in the rest of the world. You know, that little dip is there. Suppose there's a bigger dip. Suppose those crowns are bigger. That's affecting the temperature. Okay. Next, told you a long time ago that I don't use altitude of kilometers. I use altitude of 0 to 1. Okay. So I'm just going to show you very simply. It's not as trivial as what I'm going to show you, because I did it in a short length of time here. The next figure shows temperature and power versus altitude. And we know the temperature falls linearly with altitude. It's a very good approximation, and the scientists can calculate that it should be too. I mean, so it's no big surprise when temperature falls off really nice and linear. And it's pinned at that 13 kilometers, pretty much pinned there. And the power flux is an important formula that the power flux in watts per square meter for whatever distribution, whatever the temperature is, you're going to have one of these distributions. You're going to calculate the area under it, you know, this little one, and then the nesting egg, or this nesting egg. It's going to be 5.67 times the temperature divided by 100 to the 4th power. It's very sensitive to temperature. Okay, and the 4 spans I'm going to show you now. Okay, so here we have, this is going out to 50 kilometers. Here's 13. This is supposed to be a 5 here, so I don't know how that got to be 50. So here's the temperature. Straight line. Well, now from then on, this stuff out here is taking over. Okay, I mean, this is all these hot molecules out there that are looking for something, you know, looking for a mate. They're fireflies out here just banging away. They're getting hotter. Temperature there is defined by the hotness of the average molecule. Down here, they're coming through equilibrium. They're negotiating by battling it out. Okay, but it's thermal equilibrium. And so you get this. And this is the power curve. Okay, this is the line that is 20% of the atoms are below this, 40% are below, 60%, 80%. Well, 100% is out here somewhere. So at this point where I'm picking at the cutoff to be, it's 0.82. So here's 0.8, so it's right here that the cutoff is. Because this extends a little bit. You can think of what the profile here is. It's a profile here matching up with the profile here. And I didn't go through all the math, but it's basically this one by itself is going to want to go to here. Okay? So, because the other one doesn't count as far as doing anything to the center of the Earth, to the Earth level. Okay, so what do I get now? So every time when I do this thing, and I'm going to make a model of the atmosphere, and I'm going to slice it up into 50 slices. 50 slices. But I'm going to do 50 slices of Z prime, not Z. You know, I can have the average. I can make all of those have exactly the same percentage of atoms in them if I want. I did it both ways. I mixed them up to see if there was a problem. So I definitely 50 was enough. Okay. So you just get it. And so out to 0.82, it's absolutely correct. Anything after here, I just use some intuition, let's say, to finish these curves off. But everything up to here is absolutely correct. Because you know it goes to 0 here. Everything goes to 0 here. Okay. So everything's smooth. Okay, so that's what I do. I have these. And you saw, oh, by the way, you saw that was 20, 40, 60, 80, 82, okay? Okay, now, here's the crux of my work is in the next 2 sections, the spreadsheet calculations. And this is where the chemistry is turned into physics, and the physics is turned into physics, and it all looks like a circuit diagram, and you're finished. I'm basically an electrical engineer, so it's not a circuit diagram, but in a way it is. Okay, so let me just show you. There's all the work that goes into this whole thing. This picture is all the reactions taking place in one slice. This is higher Z prime. This is lower Z prime. The stuff comes in, the BBR. I'm only interested in the BBR. And this diagram, by the way, is only for one color. And I got a whole bunch of colors. So I got to do it all. I do it all in parallel. But I do this calculation for every single color, every single waveband band. And I do it for 3 different absorbers, because the absorption isn't. You don't add the absorption from each of them. 3 things are absorbing. You know, they interfere with each other. So there's a way to calculate. It's a combined absorption, a combined transmission, I should say, combined transmission. So you have this thing. I can handle 3 absorbers, and somebody could add it, but I only have 3. And so I do this thing. And in the midst of this thing, I'm taking care of the adiabatic effect. I'm taking care of absorption. I'm taking care of what's in the up and down stream that is not adiabatic and is not blanket. This is this is what's left over. The adjusted BBR out. And this is the new cumulative blanket. I add this little piece of blanket. And here it was here, and I just add them on, and there it is coming out. So the blanket's keeping getting bigger as you get closer to 0. So the blanket keeps picking up. And that's what was nice about that tent picture I couldn't show you, is you can see the blanket getting bigger as Z goes down. And when I calculate it, I do the calculations such. These calculations are beautiful. Okay. Anyway, you do this, and I do it all the slicing, and everything. I have to match all these boundary conditions, and they work great. This thing works great. And so it makes it sound easy, but it's not. I mean, so when I have this thing, when I've got all these slices, I can pull out data for every different altitude that I want. I can pump it into a little storage file automatically from the. This is all in a spreadsheet, by the way, and it comes out and it kind of put in these files, and then I can use those files. I either put them somewhere else to save them real quick, but I can make other kinds of plots out of it. You know, I use this data. If I use it right back, because the next time I run another input. Change the absorbers, for example, it's going to wipe out that file, that temp file. Okay, but that's what I do, and it works great. Okay, I mean, that's all I got to say about this thing, is that it's fine. Okay, I already said all this, and so I'm checking on everything all the time. Everything's got multiple checks. So when I'm actually adding the little bit of adiabatic effect in each little slice, all 50 of them, comes out 140. You know, I'll get 139 to 142 all the time. You know, it says that's great, and and I'm checking the blanket comes out correct all the time. I know what it should be. If I know if I make a guess on the temperature, I know what the blanket has to be. And so what I'm doing here is I'm getting I make sure that the blanket result match with the temperature result. So all I do is, anyway. It takes about 10 minutes to do a run. Everything works beautifully. Calibration plots. This is very, very important because it goes to the fundamental part of it, but it does use the calculation plots. But I'm not going to spend long on it because it was originally designed. I make a calibration plot of the absorption factor as a function of temperature. The temperature that you have, assuming that the sun is always 240 watts, or 239 watts per square meter, I assume that. The temperature is fixed by how much absorption is taking place. It's fixed by it. So I want a plot that gives me the temperature. Let me just show it to you real quickly. The temperature as a function of the absorption factor, which is 1 minus the transmission factor. And it's the transmission factor of all the stuff that's there, all these different things that are absorbing. This means combined. Okay, it's combined all there. So this is, when I do this, how do I set it up at first? Well, I set it up at first by taking a make-believe ideal absorber that absorbs the same at all wavelengths, at all colors. Every color is going to absorb the same. And now I'll make 20%, 30%, 40%. And I get a point in the curve. And once I get that curve, and then I do some real simulations, the points all pop on the same curve. So now that I've got the calibration curve and I can get this to work, I can tell myself, well, if I want the temperature to go up by 2 degrees, what's going to happen? What's going to happen here? I can tell how much more absorption without doing the run. I can get it right off of here. How much more absorption is required to do it. If I want to get to 3 degrees, I've got to get to here. Look where I am here. You know, and the biggest number is 1. Once you get past 0.88 or something, you're getting into an asymptote, and it's very difficult. You have to really load up your atmosphere with stuff to absorb because it does less and less. It's less and less efficient. Okay. Anyway, so I may just quit there. I think so. It's about 0.84 on the baseline number, and there's a slope to it. And this slope is 0.6 degrees Kelvin per 1/100th of 1 minus T Combe. The point of saying that is it changes at different places. But if I check the slope around where we're operating now, that's the slope. And it's much more predictive than looking at this log 2 of CO2, where you're blaming everything on CO2. This thing is blaming everything on everything. You know, and this is the plot to use to calculate what it needs to do. Okay, so and I can make my own thing, doubling curve. So when I did it with just CO2, and I didn't allow the other guys to do anything, it's 0.45 degrees that CO2 is doing. But it ends up being per doubling of CO2. But if I allow the others to absorb, because after all, they did get more photons working on them, then that's where I get the 1. So most of that number that we're getting of warming from 0.01 C per year, more than 50% of it is from the other stuff. But the CO2 is there. OK, I'm going to let that go now. OK, that's about what I've said. Temperature, that's really important. I can't cover it. This is I have in my recommendation it needs a MacArthur Prize for somebody to solve this. OK, it's really junk. OK, the log 2 slides. Now we're into the real results everybody's interested in. Basically, you should understand what I'm going to do right away. I'm going to show you the same thing for a log 10 and a log 2. If it's 1 degree per doubling, then the equation is delta K equals 1.0 times log 2. If it's at 1 degree per doubling, and I'm going to use a log 10 for my scale, yeah, you multiply by 3.322. And what do you get? OK. Well, I get the same result. I mean, this is log 10, and this is log 2. But when I line up my 800 parts per million, 1600 parts per million, they're the same delta K. In other words, it doesn't matter what log I use. The log 2 is just a nice number to say to people, if I double the CO2, I will get this. If you said 10 times, I'd do this. So I'll say, well, suppose you only did it 5 times. OK, so 2 is a much nicer thing. And you say, because then you can say, well, it's 2. Now let's make believe it's 8. Well, then just multiply by 3, and you got 8. Is that close enough to 10 for you? OK, so, OK. And this is the plot that originally it seemed that they were using. In the 90s, they were talking this number, which turned me off right away. 1 degree centigrade for each 100 parts per million. They're saying that's when what I call fear cum belief showed up, where they got everybody so scared, and after a while they believed it because enough people were ramming into their ears and eyeballs. And 1 degree centigrade for each 100 parts per million. Well, let's see what that is. Well, here's a case of 1 degree centigrade for each doubling, which is what I think it is. And that's what you get on a linear curve. And this is what the prediction was all through the 90s.